week. So let me share my screen and then we can continue. And yeah, there is a little presentation I'm going to show. So let's just carry on where we left off. So the last thing we did was in the previous session, we looked at cleaning up the geometry and making it watertight and creating a fluid region and a rotating region, and then bringing that into Fluent Mesher and using the new workflow to create a quality mesh. Okay, so I'm going to open Fluent. So you have Fluent. I'm going to click on meshing and I'm going to choose mesh and I'm going to select the mesh that I created last time. I can choose the number of processes. It depends on the license, but nonetheless, so I'm going to just use 4. So I can use more, but I don't want to, otherwise it consumes my computer too much. Okay, so Fluent Meshing's opening up, and it should open up the previous save state. We can then, if we need to make any modifications, I'm just going to run through a few things. We're going to discuss them, and we can then go from there. So let's just wait for this to open up, and then we will continue. You just give it a little bit of time. Okay, so something happened there. Sorry, let me just quickly go back to this. Sorry about that. Let me just quickly sort that out again. Okay. Sorry about that. There we go. So now it has opened. And this is the mesh we created last time. So I'm just going to run through it. So the first thing is we imported the geometry. You can specify what file you want to use, and then you can go from there. Then we added local sizing. We added a body sizing to the coil itself. We did a proximity so that we get at least 5 cells through any narrow channel. And then we did a face sizing on the walls of the impellers. We then created a surface mesh, which is a tetrahedral mesh initially. We then described the geometry. We specified that as both fluids and solids and voids. We did share topology, so we didn't worry about that, don't need to worry about that. We also applied an internal name to that internal boundary, so we don't need to change that, and we didn't want to share topology. And we have created our fluid region, so we don't need capping or anything like that. Then updating the boundaries, so that on the name selections, it just defines the boundary condition you want to specify. You can change that. Again, you can change that into Fluent itself, but this is just your basic setup. Ensure that at least internals are correct and walls are correct. Then the next was creating regions. It then automatically detects that there are 3 regions. We just need to specify that the coil is solid and the rotating region and the other fluid region are both fluids. Then the second last thing we did was create a boundary layer, and the definition we used was just the smooth transition. It uses a transition ratio, and we specified the number of layers, and we specified that as 10. We then created the volume mesh using the polyhex core, and we then created that. We then got a mesh quality of about 0.15. I then right-clicked and said insert new volume improve, and I specified that to 0.2. So that's my inverse orthogonal quality, and then I refined that. So we can have a look at our mesh internally. So this is our surface mesh that we see now. So that's how the boundaries are resolved. And then if we draw the cell layer within inside, we can then see what the mesh itself looks like. So you can see the boundary layers on the walls. You can see the hex core within the center, and then the polys on the boundaries or between the hex and the walls. And then there's our interface. And so you can see a fairly good mesh. You can check quality and things like that. For example, I can check my report size. Let's report the number of mesh. So let's update that. And we can see that we have 4.3, 4.4 million cells. So that's not too bad, and the mesh looks pretty good as it is. So that gives us an idea. You can also check on the quality measurements. So we can see what our quality is like. If you are a bit worried, you can, for example, go to cells and you can look at the quality. You can specify the range and find the cells that are perhaps not good enough for you, and then you can see where you need to refine further, maybe add special local refinements to those particular regions. But we don't need to do that. We have a good mesh. Its orthogonal quality is above 0.2. So with above that, we can move over to the next thing. Okay, so the one thing that you did request last time was more information about the boundary layer and how the boundary layers work. Okay, so let me get to that. Okay, so nonetheless, okay, so now basically the boundary layer is where there is a high gradient in velocity. So near the wall, where we call the boundary layer, is where there is a rapid change in velocity. So if we plotted velocity wall versus wall distance, near the wall we have a big change, and then the wall velocity tends to be the free stream velocity further from the wall that we get. So we can then do two things to this. We can plot it in a log scale, and we can create dimensional units for the velocity and for the distance. And we use the velocity, we use the free stream velocity divided by the shear velocity, and the shear velocity we can get from the shear stress at the wall divided by the density. And then the wall distance can also be non-dimensionalized to what we call the y plus, and that's essentially the distance from the wall times by your dimensionless velocity divided by your dynamic or your viscosity. All right, so with that, when you change that, you get a graph that looks something like this. This is a predictable form for most case flows. So up until a y plus of 11, there's a change, quite a big change in logarithmic. And then thereafter we get a linear scale. So there's a linear scale at the beginning, and then we get a logarithmic scale thereafter as we increase. And then it tends to go off at a bit for high y pluses. It tends to remove from that logarithmic line once again. Okay, so if we look more closely, so we have these various layers which we can associate to various forms of the flow. So the first one, where there's a y plus of less than 5, we have what the viscous sublayer, and that's immediately adjacent to the wall. Then we have the buffer layer, where it's between the linear and the logarithmic scale. And we'll talk about this region, but this region is essentially, we do not want our meshes to coincide with this. We either want it within this viscous sublayer, or we want it in the fully turbulent logarithmic law region. All right. And then you get upper limits where it starts to tend off from that logarithmic scale. But we essentially want to have these two areas that we would like to resolve in this viscous or in the fully turbulent. And we'll discuss both as we go on. Okay, so what strategies do we have? So we have two ways of actually solving for the boundary layer. The one is using a wall function, and that essentially enforces this condition on it, and it applies an empirical relationship for that profile. And we'll speak about what y plus that needs to fall into. Okay, and then the next is actually resolving the viscous sublayer, and that's actually solving, well, meshing the boundary layer and actually explicitly solving the boundary layer using the mesh, where the wall functions, you were using empirical relationships to represent what's happening near the wall. Okay, so there's a couple important things. So the first thing I mentioned, obviously, was the first, if we're using a wall function, we need to have our wall function in the logarithmic layer or in that fully turbulent region. So this, and it generally say above 60, and this upper region is generally about 300 in most cases. But the general rule of thumb is between 30 and 300. So if you want to use empirical relationships, you should have your y plus between 30 and 300. Less than 330, then we have that area where we're in the this buffer layer or blending region, and it's not accurate if we're sitting there. So we want to be in this region here. All right, so we can do that. So this 300 is also not 100% defined. For most cases, 300 is good, 250 as well. And if you have very large, high Reynolds number, that value can increase. For very large ships, for example, that y plus can be of an order of 1,000 rather than 300. So that does vary, but generally for most cases, between 30 and 300 is what you want to achieve. So if you're using a logarithmic, using a wall function, we want a y plus of 30 to 300. Okay, and then if we've actually resolving in the viscous sublayer, we want our first cell to be in this cell region here, this viscous sublayer. So ideally, we want a y plus of less than 5. That is the perfect, that is good. In an ideal world, to be honest, we want specifically if we're doing conjugate heat transfer, we would rather have a y plus of close to 1. So anything less than 5, but rather close to 1 or less than 1 is ideal. So we want our first cell within that viscous sublayer, and then we will be resolving our boundary layer using the mesh itself. So the first cell should be approximately 1, and we shouldn't have it anything different from that. Okay, so then what turbulence model should we be using? So The safest bet is what the K omega SST. And the good thing about the K omega SST is it adapts between resolving the viscous as well as the wall functions. And it automatically detects if your Y plus is less than 5, then it will automatically use the viscous model and resolve it using the cells. Where if you have it detects that the Y plus is bigger than 30, then it will solve using a wall function. So the best bet generally is to use the K omega SST, or you could, if you wanted to really modify your turbulence parameters, you could look at something like Gecko, where you then have more parameters to tune your turbulence model. Okay, so with that said, this is obviously what it would look like for a wall function, where there's a lot going on, but we have only one cell representing that gradient. So we need some form of empirical relationship. And then if we're resolving the sublayer, we have a fine mesh, and that mesh captures the gradients and captures the shape of the boundary layer. Okay, so how does this work? So where can we use this and how can we make sense of this? So I'm going to use a little bit of an example. So we have airflow at 20 meters per second. We have the density and we have the kinematic viscosity, the dynamic viscosity. From that, we can get a Reynolds number, and from the Reynolds number, we can deduce if it's internal or if it's external flow. We can deduce if it's laminar or turbulent. Obviously, if it must be the turbulent regime for this boundary layer, turbulent boundary layer to apply to. Okay, so basically the first thing we do is we rearrange the Y plus so that we're solving for Y value, so that we can find the size that we need to enable to get the Y plus we require. So we can then target the Y plus, say, let's say, for example, 1, and then we can find the Y that we need. So the first thing we need to do is non-dimensionalize our velocity, and we can use that using the shear stress and the density. And to do that, we can use the shear stress using this equation. And this equation is a standard equation for the wall shear stress using the skin friction coefficient. And the skin friction coefficient can be calculated using this relationship. This relationship is well known generally for external flow. That's Reynolds number is for the length for, say, example, an aerofoil or a chord length or something of a wing. And then if you're doing internal flow, you would use a friction factor closer to this to get the friction factor. Yeah, once we have the friction factor, we can find the wall shear stress. And from the wall shear stress, we can find the non-dimensional velocity or the wall velocity, shear velocity. We can then find the Y value. So if we, for example, use a Y plus of 50, we substitute that in, substitute viscosity, the velocity non-dimensionalized, and the density, and we get a cell size. So this is approximately the cell size of our initial mesh. So if we were, for example, generating here, we could go to offset method and specify uniform, and then specify this value that we've calculated here. And that is not the Y plus you should be using. It's a good starting point, because obviously this velocity is going to vary throughout your domain. So you might need to vary your Y plus accordingly. And I'll show you a method later on how one can achieve that. But this is at least a good starting point if you're doing things like aerofoils or external flow or flow in a pipe, and you want to know an approximate Y plus or Y cell height that you need for a particular Y plus. Okay, with that said, we then completed the mesh. I'm happy with the mesh. It looks good. The boundary layers look good. There's not such a big jump between the outer boundary layer and the next first poly cell. So overall, I'm pretty happy with this. We can then move on. So as I said, we could switch this offset method to uniform, and then you would have specified that calculated height that we used. Okay, so the next thing we do is we switch to solution. Obviously, you should write your mesh. It's a good idea to write out your mesh so that if you want to go back and edit it and make modifications, you have your history and you can make modifications without rewriting everything. Okay, so I have saved it already, not to worry. So I'm going to select switch to solution, and that's going to then bring me up to my Fluent console, where I can then specify my boundary conditions, my material properties, and things like that. Okay, so let's allow that to open for a little bit, and we can. Is there any questions with regards to the boundary layer and Y+? Hopefully, I have covered that. If you have any questions, feel free to ask. Okay, and there is a spreadsheet. I have a spreadsheet that I'll share with you. I'll put it in that file that we've been using. And there is a nice spreadsheet. It's fairly straightforward. You specify a velocity, density, and viscosity, and a Y+, and then you can calculate the value from there. Right. So that is opening up. It's busy processing the results, processing the mesh and going from there. All right. So it seems to be open. So I'm going to run through a few things and just show you what Fluent looks like in general. Okay, so this is Fluent. On the side here, we have an outline view, and there's various options you can use in here to set up your boundaries and your conditions and your cell zones and things like that. And then you have also a number of toolbars, and each toolbar has a set of tools associated to it. So the domain, anything related to the domain, the mesh, units, zones, interfaces, adapting, meshing. If you want turbo interfaces, things like that, you define in your domains. Then in your physics, we would specify operating conditions, what type of physics, if there's energy, multi-phase, things like that. It will specify our materials that we'll be using, and then cell zones, what conditions in the different cells, and then obviously our boundaries, so our inlets and outlets, what conditions we want there. Then the next important one is the solution. The reports where the controls and these methods we'll discuss briefly, but that's only if you're really having convergence issues. You can play around with those. Then initialization we'll discuss later on, and then finally just your calculation inputs. Okay, so that is the main toolbars. We're going to start off with this toolbar on the far left, and that's domain. And we're going to first show the domain. So we can show the faces, we can specify. So these are the names that the different regions and name selections we created. So it's important to create good name descriptions or name selections so that you can use it further to apply conditions in Fluent later on. Okay, so I can, for example, I'm going to look at the coil, the blades, and I'm not going to show the shell, and I'm going to display that. And then we can see the geometry. If I wanted to show the shell, I could also show the shell, and that's what our geometry looks like. Okay, so that's fine. So our geometry looks good. The next thing I want to do is I'm going to check my info. I can check the size of the mesh just to confirm it's the same as what I had in the previous one. And we can see 4.38, so that's the same. So everything's good there. Then we can do a mesh check. We can say perform mesh check. Just check what our domain extents are, if those make sense. if maybe there's an order out, if we're using the wrong units. Then also just checking the minimum volume shouldn't be 0. And if it's 0, then there is an issue. So it looks, everything's good. There's a volume, a total volume, and my minimum and maximum coordinates make sense. Then the next thing is I can just evaluate my mesh quality to double check, and I can see my mesh quality minimum orthogonal quality is 0.2. So that is a good mesh. Anything above 0.1 is considered good. So 0.2 is considered a nice mesh. So I'm happy with that. We can then move on. If you really wanted, you could do an improved mesh quality, but it's unnecessary. Okay, so we've checked that. So the next thing I want to do, which is the units. And then we can specify what units we want to use. So the first thing is I want to use my angular velocity and I want to use RPM. And then I want to go to my temperature and I want to use degrees Celsius. I can select that and I can close that. You can change any unit you want. You can add custom units if you want to as well, and you can go on from there. Okay, so this is pretty much everything I need for now. I don't need to combine any zones or do any mesh interfaces. I don't have any turbos, so I'm not going to worry about any of those. So I'm going to move over to my physics tab, and the first thing is my operating conditions. So this is my default reference pressure. So I'm going to specify at atmosphere of 101325 pascals. I'm going to specify gravity and I'm going to say negative 9.18. I can see here the vertical direction is Y. So obviously I want to make that negative 1.8. So I switch that on. Then the next thing is to switch energy on because we want to solve, we have an element here and we want to solve energy. So I switch on energy. Okay, and then the last thing is I could also switch on energy here. I could have switched it on using this. I could have double clicked here and switched energy on there. So you can use this outline tree or you can use the toolbar. Okay, so the next thing I'm going to do is talk about the multi-phase. So I have two inlets and they're different fluids that are coming in. Okay, so before I actually do that, I want to go to my materials and I want to create some materials that I'm going to be using. So I'm going to look in my fluid database and I want to look for just water liquid and I'm going to copy it across. Okay, so then I'm going to create another one. I'm just going to call that slurry. I'm going to delete the chemical formula. I don't need it. Let's say that's 1200 and the rest. Let's say the viscosity is a little bit higher, say it's at 0.1. Okay, then I can click create. Do I want to overwrite water? No, I don't. So I can now check that I have both slurry and I have a water in there and my properties are different for both. Okay, so now I have added, there is other databases available. It depends on your the license you have available, but there's a granted database where there's a much more comprehensive list of properties. Then there's also a user-defined database. So if you've created any properties and you've saved it to a database, you can then access that later on. Okay, so I've created the fluid, so now I can go to multi-phase, and the multi-phase I'm going to be using is the mixture model. Okay, so the mixture model is best. So volume of F, VOF, or volume of fluid is good if you have an interface between, say, air and a liquid, a gas and a liquid. Then also Eulerian if you want advanced inhomogeneous modeling. Mixture model is a homogeneous model. It works fairly well in most cases. So I'm going to apply that and I'm going to have number 2 Eulerian phases. Once I've applied that, we can see now there's additional properties that have come in. So we can look at those additional properties such as my molecular weight, things like that. and enthalpy, reference temperature, things like that. All right, so I'm not going to worry about those. I'm going to leave it slurry. I'm just going to leave it as it is. Let's just copy that over to the slurry here. Okay, good. So now I'm back into the phases, and I'm going to specify my initial phase. I'm going to select as water, and my secondary phase I'm going to select as slurry. Okay, we can specify a diameter. We don't have to. By default, it's very small, and that's fine. And I'm going to apply that, and then I'm going to now create a multi-phase simulation where there's 2 phases. And we can monitor the mixing of that. Okay, so I've created that, the model I'm going to use. I've switched on energy. Viscous model by default is the K omega SST. If you really wanted to, you could look at K epsilon, but be careful which one you use, if you're using the modified wall functions or not. And then another option would be the gecko. It's a modified K omega, and it's just got a few more parameters that you can tune to better resolve your boundary layer. But for first simulation, K omega SST is probably your best bet. So we'll leave it at that. Okay, so materials we've defined. I can remove this air if I wanted to, but I don't have to. Then the solids, I'm going to just leave as aluminium. Okay, the next thing is my cell zones. And the cell zones is where I'm going to define a few other things. So I'm going to double click on the cell zone, and I'll show you what it brings up. So there's a few things here. So I'm clicked on the fluid rotating. So that's a rotating regions, and I'm going to use a frame motion. So it's not going to move the impellers. It's rather going to move the fluid and see what the results would be. So when it enters the domain, it adds a rotational component, and removes, comes out of the domain, it removes that component. Okay, there's other things we'll discuss, like source terms. There's porous zones. So if you do have a porous media, you can add a porous zone. So just note that if you do want to do a porous zone, you need a separate zone for that. So you need to break up your geometry into small components and then specify that. Okay, so I'm going to specify, my default is in my, I'm going to specify, it's going to rotate in the positive, the negative Y. So I'm going to specify negative Y here, and let's specify 30 RPM as my rotational speed. I can then apply that and go from there. That's all I need to do for my rotating on the cell zones. And the next cell zone is on the solid, and that I want a heat source. And I'm going to go to my source terms, and I'm going to add one heat source, one energy source. I can then specify a constant. You can see the default units is watts per meters cubed. So you need to define what the unit source is for this. I'll show you a trick. So instead of using that, I'm going to use an expression. I'm going to specify expression. I'm going to select the function, and I'm going to create an expression from there. Okay, so I want 10 kilowatts. So I want to say 10,000 watts per cubic, and I just want 10,000 watts. It is unit sensitive, and then I want to divide that, and I'm going to use some function, mathematical function, and I'm going to use a reduction, and I'm going to sum up, and it says, what am I going to sum? So I'm going to sum up, I'm going to use a variable mesh, and I'm going to say cell volume. Where do I want to sum it up? So I go to my location, and I'll go to location, cell zones, and I want it in my coil. So in location, and then I can specify what type of weighting I want, if it's mass, area, or volume. So I'm just going to use a default. So I'm going to deselect that volume. So it should without any weighting. Okay, so I've summed that up, so I can then select OK, and then I've got a energy source. If you really wanted to, you could create a named expression, for example, and I could have called that heat source. And I'm going to say 10,000 kilowatts. And I'm going to declare that. And then in my energy source, instead of defining the 10,000 here, I can rather use that expression, the heat source. Then I can use that. And I only need to change, if I want to change my heat source, I can change it here and it will change everywhere else where it's referenced. So that's a little trick to make that slightly easier. So I've defined my heat source and I've defined it on my coil. Okay, so I've defined my cell zones, I've defined where my rotating region is, and defined where my solid region is. And obviously I want a heat source in the solid because it's a heating element. So I added a volume heat source to that. Okay, so the next thing is we need to go to our boundary conditions. And it's nice to work top to bottom in this tree, and we can look at our inlets. So I have a velocity inlet. I'm going to change those to type. I'm going to rather have a mass flow inlet. And it's up to you what you want to do. It doesn't matter. Okay, so to just double check, we want to see, okay, what phase? My phase 1 was water. Phase 2 was my slurry. Okay, so I go to my mass flow and I want my phase 1. So if I double click the mass flow, it just gives me a name. Okay, so I want to specify normal to boundary, apply that. Turbulence intensity, let's specify it at 10. Hydraulic diameter, we could specify a hydraulic diameter. I can't remember the diameter size, but let's just use that, leave it as turbulence. Preferably I would go hydraulic diameter. I can't remember, let's just say 0.1. That's not much of an issue. Okay, well, I can check in my geometry. Okay, so with that, I'm just going to apply it to both of them. I want that normal to my boundary, and I want 10. Let's just keep it as a viscosity ratio. Okay. Ideally, you should use hydraulic diameter, but as I said, I don't have that information right now, but I would rather get it and then go from there. Okay, so next one, I'm going to select my phase and I'm going to define my mass flow. Once again, I'm going to use an expression, and this time I'm going to say I want 10 liters second -1. Okay, that's the format you have to use, so that's liters per second. And I'll obviously, to convert mass flow, volume flow to mass flow, we times it by a variable and we times it by the density. Okay, so I should probably do some volume expression here. So let me say mathematical expression. And we want obviously the density. So I'm going to say area average, and I want the area average. Or actually, I could just say I want my variable to be density there. Okay, and that must be density of phase 1. Okay, then I can apply that. Okay, no, sorry, I should have applied my thermal boundary, and I want that to be 20 degrees Celsius on that inlet, and you apply that on the boundary and you specify the mass flow rate. So phase 2, I obviously want a mass flow rate of 0 because I don't want any flow on that. Then the second one, the mass flow rate of phase 1 should be 0, and I want to make sure it's normal to the boundary, and that is at 15 degrees Celsius, my inlet, and I'll apply that. Then I'll go to my phase 2, and I can then also specify an expression. I can say this is 15 liters per second times my variable, and I want my density, and that's obviously of phase 2. Okay, so that's applied, and I can apply that as well. If I wanted to, I could have created a name selection representing the value, and then instead of changing it in this phase, it would be easier to change it under the named expression. Okay, so that's good. We can apply that, and we can then move over. Okay, the next thing is we need to just look at the outlet. Outlets, I just want standard atmospheric, so I'm going to have gauge pressure. So this is the static gauge pressure at the outlet, and then this information below is what happens at the backflow. So what is going to happen if there's reverse flow on there? Then it will be total pressure, and it will use these and this thermal. So let's just say that's at 20 degrees as well. All right. So we're good with that. We can apply that, and we can close that. Then the only other thing is I need to specify for the walls. So the walls and the impeller, I'm going to say multi-edit, and I can edit in at once. And I'm just going to run through this, but essentially this is, it says it's a stationary wall relative to adjacent cell zone. So these walls are within a moving cell zone, so therefore they actually are moving, so they're stationary relative to the cell zone, but because the cell zone it is also moving. So if you really wanted to explicitly say it, you could say moving wall absolute. You can specify all the shafts, and you can specify that it's direction rotational, and we can specify that it's in the -1, and I think it was 30 RPM. Okay, so you can also explicitly define that, and we can apply those. So all of these guys now have that, and that is generally the better approach to actually explicitly define it. So we have a 30 RPM in the -y direction for those 3 faces. Okay, and then all the other walls should be non-slip. The coil, it's outside the region, so it should be stationary as it is. Okay, so that's everything on on that side. So the next thing is I need to define some reports, and then I'm going to go to my solution. I'm going to go to report, definitions, new, and I'm going to say surface reports, and I'm going to use mass weighted average. And that mass weighted average, I'm going to say TSAV outlet. Okay, and then I can see I want it at my temperature, my static temperature. I want it of my mixture, and I want it at the outlet. I can then create a report plot or a report file where I can monitor it. I can create it later on if necessary, but let's create a report plot so that we can monitor that value while it is solving. Alternatively, monitors, we can check our residuals. These are residual criteria. By default, I'm going to leave them as they are. If you want to make them more a higher criteria, you can reduce these so that it solves a bit longer and gets a better, more accurate solution. Okay, so that's with that. The next thing I want to do is create cell registers, but I want to create a cell register for my Y+. So to do that, I need to initialize. I go to the initialize. I can go to my hybrid options. And this is my standard initializations. And I can see what my values are. I'm going to specify it at 20 degrees initially. And it is of phase 1. I want 0 to phase 2, 0. So therefore, phase 1 is 1 volume fraction. So it's initially filled up with only water at a 20 degrees Celsius. I can then select initialize, and then it's going to assign all the cells these conditions that I've specified. There is other methods you can use depending on what, if you're doing transient analysis or steady state, or if you want to use the hybrid analysis initialization, you can. Okay, so let's allow that to just go for a moment. So it's just creating my initialization. It is moaning about a few things, but don't worry about that for now. Okay, we can see our report plot that is generated. So you can create report files if you want to, that spits out information that you can read later on. Okay, so that's initialized. So I'm now going to create a cell register. I'm going to go new, and I'm going to say Y+. I'm going to specify Y+, and I'm going to say important. And then I'm going to specify which cell zones. So I'm going to, important is my blade and my coil. Let's just also say coil. And we can say, let's say between 0.1 and 1. I can then save that. I can then have a cell register. If I want to plot where those cells are, it will show me. I can then go back to my domain, and I can go to adapt, refine, and coarsen. Then under my criteria, I can specify my cell Y+, and I want a dynamic adaptation so that after every 20 iterations, it's going to adapt my cells. So this is a good way to refine your boundary layer without manually doing it, rather using the adaptive mesh refinement to solve it for you. Okay, then if you also want other adaptations to base, for example, if you're doing high Mach numbers and you want a pressure wave, you can do refinement criteria based on gradients of pressure, for example, and then you can refine that. The only thing is adaptation control. You can only specify one adaptation at a time. So you would need to, for example, run a number of iterations where you adapt your Y+. Once you're happy with your Y+, then you can change your adaptation controls, for example, for a gradient method, and then adapt accordingly and go from there. So I'm just going to specify my criteria as my Y+, and I'm going to, for every 20 iterations, I want it to dynamically refine based on those conditions. Okay, if I wanted to, I could have adapted initially, but I'm just going to specify it once it actually starts solving. Okay, and then the last thing I need to do is go to my auto save under calculation activities. One thing is Fluent does not save. You need to save manually. So you need to either save manually, or you need to use this auto save method. So I'm just going to say I want to save every 100 iterations, and I only want to keep my latest 5. I don't need all of the data. I only need the latest 5, and I'm going to specify a name. I'm just going to call that tank GZ, and it will automatically save in the file that I have. Then I'm going to select OK, and then I'm good to go. So the next thing I would do is I would select this change the number of iterations. So let's say I want 10,000 iterations, and then I would click the solve button. Okay, so I'll allow this to solve. I just want to show you what you'll visualize and what will come up while it is busy solving. So it might take a little bit longer on my computer because it's a big mesh. for the number of CPUs that I've specified, but let's allow that to just go on. So yeah, so that essentially covers everything that I wanted to show today. So it's basically setting up. I showed you that there's multi-phase, how to set up multi-phase, how to do rotating regions, how to add a heat source, how to use expressions and named expressions, and then obviously defining report definitions so that we can monitor our results as it's solved. Okay, so it is busy thinking, so I'll allow that to think. If there are any questions, I think it's a good time to speak to that now.
Okay, so thanks everybody. Thanks, Keith. As Keith said, is there any questions from anybody?
Yes, got a question. I was just wondering on the coil. Just for understanding, is that uniform heating all across the coil, or it could have a different, like a gradient right across? I just wanted to find out.
Okay, so you probably could with some form of UDF to have a gradient, but as the way I defined it, it is uniform. So it's a uniform volume heat source throughout the thing. So that's why I defined it based on it. It's based on volume. So if you wanted to, you could have added a gradient, but it would probably be more with a UDF. Then straightforward, or you would have to split up your coil into multiple zones to apply different boundary conditions. Then I'm just looking in the questions. Okay, so the mass flow one's answered. You could have specified a constant. I just specified it as a volume flow rate because in most practical applications, you will be given a volume flow rate in most practical applications. Or generally on most data sheets, they give a volume flow rate. So I generally just showed you a way to define the volume flow rate on a mass flow rate boundary, but that doesn't matter. It is up to you how you want to define that. You could have specified a velocity and a constant velocity if necessary, or you could have used an equation based on velocity, area, and density to calculate a mass flow rate, for example. All right, so then also recommended couple monitor points within the 3D zone. Yeah, so there's definitely the more monitor points you have, the better. So one important thing is monitor points can be used for visualization purposes only. And I think it's very important to not judge your convergence only on residuals, but you look at both your residuals and the monitors of interest. So if I'm interested in the outlet temperature, I should monitor that and see when my outlet temperature is converged and is no longer changing. I can also add a criteria for convergence based on my monitors. So it's good to add monitors, things like on 3D zones like average velocity, maximum velocity, average pressure, maximum pressures. Those are also good things to monitor. So you can go wild with a number of monitor points, but the important thing is monitor what you are interested in and base your convergence on that, as well as based on both your residuals as well as your cell zones, your monitor points. Yeah, it looks like it's taking very much its time. Okay. Then, yeah, I don't see anything else. Any other questions up till now? I'm going to solve this over the next week. And then I will show you what the results look like, and we'll do a bit of post-processing next time to visualize the result. but essentially I was showing you today how to set up. And with the new meshing and the new Fluent, it has made it a lot easier to create a CFD job. And there's a lot of tools available to make your life easy and as easy as possible. Okay, so if there are any other questions, feel free to ask. Okay, so a detailed and deep dive into some of the capabilities of Fluent. Okay, so I think that's, I could probably be here for a very long time discussing the capabilities of Fluent, but Fluent can do anything from single phase to species to multi-phase. It can do reactions, it can do solidification, it can do melting or phase changing. It can do boiling, things like that. It can do rotating regions. It can do moving meshes. It can do heat sources. It can do, I'm trying to think what else there is. But in terms of the physics, there's a lot. So I think I can look at something a bit more detailed for next week, just give you a better overview of the capabilities. But there is a huge list of what it can do. But if you can think of it, you can do it. Essentially, there is also means of ways of using scripting to get around things that aren't built into Fluent. So there are means of ways to pretty much do anything you can think of in terms of fluid flow and conjugate heat transfer. Or not even just fluid flow, solid and gas and... Okay, cool. So, okay, now then you're actually happy with that. Okay, so I think that's good. You can see it's starting to solve now. Okay, so there's one more question. Okay, so there is a number of ways to simulate a rotating region or the movement of, say, some blades. Okay, so the first way is by explicitly modeling it, where you would actually have a moving mesh and you would have to have a transient analysis, and the mesh would move and the impeller would actually move then, because the mesh, that rotating region in the middle, is actually moving, and it calculates accordingly. So that is the one way, but the problem with that is it has to be transient, and the time step generally has to be very small, and that generally takes a long time to solve. So based on just simplifying it, we would rather look at a different approach. And that approach is what we call the rotating region, or a frozen rotor approach, or a frame motion approach. And the way that works is, instead of moving the geometry, we move the fluid in the opposite direction to what the geometry would be moving. So as soon as the fluid enters the rotating region, it adds the component of velocity due to rotation, and then it will basically, as if you were standing on the impeller and watching the fluid flow over you, instead of you standing outside and watching the impeller spin. So the frozen rotor is rather as if you were standing on the impeller and seeing the fluid flowing over you. So that is the approach on the rotating region. The reason why we go for that, it's a cheaper approach in terms of capabilities. So, and in terms of solving time. So it's going to be a lot more quicker. You're going to get results sooner. So you can evaluate the design in a lot shorter space. So generally, for your first order calculations, I would look at something like the frozen rotor approach, or the motion frame, before using a motion. All right, and then maybe a bit far-fetched, but could we induce rotational flow using source terms. So yes, you can mostly, that is all it is doing essentially, is adding a rotational source term to the fluid as it enters that region. And obviously you would need to add balance, momentum, and energy when you go from the one point into that region. So that is all that Fluent is doing in the background, is inducing that source term. So if you wanted to do it manually, you would have been able to do that using momentum and energy source terms, using a UDF, for example. So that is definitely possible. Okay, so you can see this is starting to solve. There are a few other errors, but this is slowly reducing, which is a good thing. So the turbulence viscosity generally means your mesh is too coarse or the fluid is too slow for this particular thing. So generally this occurs at the beginning of your simulation. If it's still there after a long time, then you should worry. But if it starts, you can see mine is reducing every time step, so that's a positive thing. Then we can look at our residuals, and we need to monitor our residuals. Ideally, you want them to reduce constantly until you get to a specific criteria. A lot of the time when there is transient behavior, one thing about the standard Fluent steady state solver is actually I can't go to that, but it is actually a pseudo transient. So it uses somewhat of a large time step to do the calculations. So we can then calculate that. We can reduce our calculation times or our values to get a better convergence. But we would monitor that, and we can play around with our methods and our controls if we are struggling with convergence. But again, as I said, we shouldn't monitor convergence only based on residuals, because, for example, if there's transient behavior occurring, then our residuals will never actually end up converging. You would have to create a very small pseudo time step for that to actually dissipate and for it to converge properly. So in that case, it's best to look at the monitor points. Okay, so I think that's it. I'll let it solve, and next time we can look at residuals and we can further analyze and plot results and go from there. And we can look at the results and post-process. I think this is my last call on questions. If there are any more questions, I think this is the last chance. And if there's anything else you would like me to show next time, feel free to send us an email just to request it, and I will see if I can do that for you. So I hope you enjoyed that. I hope it was informative. I hope you got some valuable information out of it. But the idea is to show you that creating CFD is a lot easier than it used to be, and it's becoming more accessible for your general engineer or the general person as well. Right, but yeah, thank you. I hope you enjoyed it, and thank you for your time. I hope you enjoy your afternoon and weekend.
Okay, thanks a lot, everybody, and